In the silent depths of the cosmos, galaxies drift like luminous islands in a dark sea, their light traveling billions of years to brush against the eyes of the observer, carrying whispers of an ancient universe. Between them, space stretches vast and empty, a canvas of shadow punctuated by pinpricks of light, and the faint hum of the cosmic microwave background whispers of a time when the universe was young, dense, and incandescent. In this immense stillness, there exists a question so simple and yet so terrifying that it trembles at the edge of comprehension. The universe is expanding, but into what? If space itself is all that exists, what does it mean for something to grow, to stretch, to unfold? It is a paradox that confounds the mind and stirs the imagination. The cosmos is like a balloon, endlessly inflating into nothing, its surface stretching without limit, or like a painting whose edges retreat forever, leaving the viewer suspended in vertigo and awe. The familiar anchors of inside and outside, beginning and end, dissolve in this contemplation. Humanity instinctively seeks a frontier beyond the known, a place beyond the universe itself. Yet there may be no such place, only the infinite unfolding of the space we inhabit. The thought is both beautiful and unsettling, invoking a mixture of wonder, fear, and contemplative melancholy. Yet, it is precisely this tension between what can be observed and what cannot be grasped that draws curiosity onward. It is a journey through discovery and shock, through mathematics, observation, and imagination, tracing the expansion of the cosmos, the acceleration of space, and the philosophical weight of a universe without exterior. In this voyage, science becomes a lantern in the dark, illuminating a reality that cannot be touched, a universe that stretches into the unknowable, and a question that remains eternal. If the cosmos is all that exists, what, if anything, lies beyond its reach? If you are new here, join the journey, like, subscribe, and let's begin. Long before the universe was understood as a restless, ever-stretching tapestry, it was imagined as static, eternal, unchanging. The night sky was a frozen portrait, galaxies and stars suspended like diamonds upon black velvet, timeless and constant. For centuries, astronomers believed that the cosmos was fixed, a serene and unyielding expanse, impervious to motion beyond the slow drift of planets and wandering comets. Yet in the quiet of the 1920s, a series of meticulous observations began to unravel this comforting illusion, revealing a universe that was anything but still, a cosmos in motion, stretching outward with silent insistence. At the heart of this revelation was a man named Edwin Hubble. Stationed at the Mount Wilson Observatory, perched high above the haze of Los Angeles, Hubble peered into the depths of the heavens with a new clarity. His telescope, the 100-inch Hooker reflector, was among the most powerful instruments of its time, capturing faint glimmers of light from distant nebulae. These were not nearby clouds of dust and gas, as many still believed, but galaxies, vast collections of billions of stars, each receding into the unfathomable distance. By measuring the light that reached him, Hubble detected a subtle yet profound signature, a shift toward the red. The wavelengths of starlight were stretched, shifted, as though the universe itself were pulling the light apart, whispering of motion away from the observer. This redshift, as it would come to be called, was more than a mere curiosity. It was a clue, a cosmic fingerprint revealing that the galaxies were not stationary, but fleeing, each one moving faster the further it lay from Earth. Hubble meticulously catalogued these velocities, measuring the spectral lines with spectrographs that trace the fingerprints of elements across unfathomable distances. It was painstaking work, conducted in the quiet hours before dawn, each observation a note in a growing symphony of evidence that the cosmos was alive with motion. When the data were plotted, a startling pattern emerged. Distance and velocity were proportional, linked in a precise and undeniable relationship. The universe was expanding. Before Hubble's observations, this notion had been hinted at in theory, but dismissed by most as speculative. In the 1920s, cosmologists like Alexander Friedmann in Russia and Georges Lemaitre in Belgium had begun to explore the mathematical consequences of Einstein's general relativity, and within their equations, the seeds of expansion were already visible. Friedmann's solutions suggested a dynamic universe, one capable of growth and contraction, while Lemaitre envisioned what he called the primeval atom, a theoretical beginning from which all cosmic motion unfolded. Yet these ideas, elegant as they were remained largely abstract until Hubble's redshift measurements provided the first empirical confirmation. Theory met observation, and the quiet certainty of centuries began to unravel. What astonished the scientific community was not merely the discovery of motion, but the uniformity of that motion. The galaxies were not fleeing in random directions or clustered flows, but in a pattern that suggested expansion was pervasive and isotropic. The cosmos was not expanding around the Milky Way, nor were we privileged observers at the center of some cosmic outflow. Instead, every observer in every galaxy would perceive the same recession. The universe itself was stretching like a vast fabric, every thread pulling outward, revealing a dynamic cosmos that defied common intuition. The historical weight of this discovery was immense. The prevailing worldview, inherited from centuries of Newtonian and classical thought, held that the universe was static, eternal, and unchanging. Even Albert Einstein, in formulating general relativity, had introduced the cosmological constant, a mathematical contrivance, to ensure that his equations described a steady-state cosmos. To witness a universe in expansion was to confront the limits of human expectation, to acknowledge that reality could surpass imagination, and that our assumptions about permanence were fragile. Hubble's own path to discovery was grounded in patient, deliberate observation. At Mount Wilson, nights were spent capturing the faint smudges of light from spiral nebulae, cataloging their spectra, and measuring their distances using Tethys variable stars as cosmic yardsticks. Each calculation was a labor of precision, each data point a testament to human curiosity. As the evidence accumulated, the pattern became undeniable. A steady, accelerating recession that left no corner of the visible universe untouched. Yet the acceptance of this new cosmos was not instantaneous. The notion that space itself was expanding required a conceptual leap beyond familiar experience. Skeptics questioned whether the redshift reflected motion at all, or whether unknown processes within the galaxies themselves could distort light. The scientific community, cautious by necessity, scrutinized every measurement, repeated every observation, and debated the implications for decades. Only gradually did the evidence solidify, and the revolutionary idea that the universe itself was growing, stretching, and evolving began to replace the comforting certainty of a static sky. In the decades that followed, Hubble's law became a cornerstone of cosmology, a simple yet profound statement. The speed at which a galaxy recedes is proportional to its distance from the observer. From this law emerged an estimate of the universe's age and scale, a framework within which the expansion could be understood and measured. Observations of ever more distant galaxies pushed the boundaries of the observable universe, revealing structures and motions that confirmed the uniformity and pervasiveness of expansion. The cosmos was alive with motion, yet governed by a silent order, a rhythm traced across billions of light years. The implications extended far beyond astronomy. To consider the universe as expanding was to imagine a beginning, a moment when space itself was condensed and the seeds of matter and energy were unified in a singular origin. Hubble's observations, when coupled with the theoretical insights of Friedmann and Lemaitre, laid the groundwork for the Big Bang model, suggesting that the universe had emerged from a state of extraordinary density and temperature. Yet even as this model gained acceptance, the fundamental question persisted. If the universe is expanding, what lies beyond it? Into what does space itself stretch? As the 20th century progressed, each new observation reinforced the sense of a cosmos in motion. Galaxies trace silent arcs through the vast darkness, their light traveling billions of years to reach our instruments. The cosmic microwave background, discovered decades later, confirmed a hot, dense beginning, a relic radiation permeating every corner of space, whispering of expansion and of time itself unfurling from a primordial moment. The uniformity of expansion, now measured across scales unimaginable to Hubble, suggested a universe governed not by chance, but by the deep architecture of space-time itself. Even in Hubble's era, the philosophical weight of the discovery was felt. To witness the universe in motion was to confront the fragility of human perspective, to realize that Earth occupies no privileged position in a cosmos that stretches endlessly. Observers in distant galaxies, Hubble's law implied, would see the same recession, the same inexorable expansion. The universe was not centered, nor bounded in any conventional sense, and the very notion of a cosmic edge seemed to dissolve. For scientists and philosophers alike, the implications were both exhilarating and disorienting. Mount Wilson Observatory, with its quiet corridors and the hum of its instruments, became the cradle of this revelation. Hubble's meticulous measurements, each spectrum captured and analyzed, were the threads that revealed the first glimpse of the universe as a dynamic entity. It was a slow awakening, a process measured in years and decades. And yet the truth emerged with undeniable clarity. The cosmos is not a static painting, but a living canvas, expanding, stretching, unfolding in a rhythm that continues to this day. The discovery phase of cosmic expansion was not merely an accumulation of facts, but a transformation of human understanding. It bridged theory and observation, married mathematics with measurement, and invited a contemplation of the infinite. The universe, once imagined as a fixed expanse, was revealed as a restless, breathing entity, stretching into realms beyond comprehension, governed by laws both elegant and mysterious. And within this revelation lay the seed of a question that would endure for generations. If the universe itself is expanding, what lies beyond? Into what vast, unknowable expanse does the cosmos extend its silent reach? In the quiet aftermath of discovery, Hubble's telescope continued its vigil, tracing the paths of galaxies as they drifted outward, distant and luminous against the black velvet sky. The spectra and redshifts, once obscure data points, had revealed a truth that reshaped our understanding of reality. Space was not empty and immutable. It was dynamic, alive with expansion, and humanity, looking outward from its tiny vantage, glimpsed for the first time the restless rhythm of the cosmos, a motion both magnificent and humbling, a mystery that would shape the questions of every generation to follow. The discovery phase was a beginning, a quiet overture to the deeper investigations yet to come. In the shadows of Mount Wilson, amidst the hum of the telescope and the patient dedication of astronomers, the universe revealed itself as a living, expanding entity, stretching outward into a darkness both terrifying and sublime. And though the scientists of the 1920s could measure the motion, they could not yet grasp the full implications. The question of what lies beyond the expanding universe, the nature of the very fabric into which it stretches, remained, and remains still, the greatest of cosmic enigmas. The moment the cosmos revealed its motion, the shock rippled through the minds of scientists like an electric current through still water. The universe, long imagined as a static expanse, a grand stage on which the drama of stars and planets unfolded, was not fixed. Space itself was stretching, expanding, carrying galaxies along in a silent, inexorable flow. To ordinary intuition, this is almost impossible to grasp. We live in a world where motion is relative, where objects move through space, but the very fabric of space stretching beneath them defies the familiar rules of experience. It is not a river in which galaxies drift. It is the river itself that lengthens, flowing into dimensions unseen, carrying everything along without a center, without a shore. Albert Einstein, whose theory of general relativity had so elegantly described the curvature of space-time, initially recoiled from this implication. In the equations he first formulated, gravity would tend to pull the cosmos together, leading to collapse or equilibrium. To preserve the static universe he believed in, Einstein introduced the cosmological constant, a term that acted as a repulsive force to balance gravitational contraction. Yet with Hubble's observations, that constant became redundant, a mathematical patch to a universe that did not exist. Einstein would later call it his biggest blunder, a rare admission of error, yet it underscores the profound dissonance between human expectation and cosmic reality. The universe was not only dynamic, it was expanding in a manner that seemed to mock the certainty of centuries of thought. The implications were both subtle and staggering. Distant galaxies, receding under the influence of cosmic expansion, do so at speeds that can exceed that of light. This is not a violation of Einstein's relativity, which forbids objects from moving through space faster than light. But it is nonetheless deeply counterintuitive. It is space itself, the medium through which motion occurs, that is stretching, creating the appearance of superluminal velocities. Light emitted from these galaxies takes billions of years to reach us, yet the galaxies themselves continue to flee, carried outward on the ever-lengthening fabric of the cosmos. Observers attempting to reconcile this with classical physics experience a profound vertigo, a sense that the universe is less a stage and more an infinite, breathing organism. The psychological impact on the scientific community was immense. Suddenly, The universe was not a bounded container, a celestial sphere with edges or walls, but an all-encompassing fabric without boundary or center. The familiar notions of inside and outside dissolved, replaced by a conceptual framework in which every point expands away from every other. There is no privileged vantage, no observer occupies the center. To visualize such a cosmos is to confront a kind of existential vertigo. The ground beneath perception stretches endlessly, carrying every galaxy, every cluster, every photon along with it. The universe became simultaneously intimate and incomprehensible, a network of motion without limit, a lattice of light and distance expanding into the unknowable. And then there is the question that haunts even the most careful minds. If space is expanding, what lies beyond it? The very notion of beyond strains language and intuition. Beyond implies a container, an exterior, a dimension into which something extends. But the universe is defined as all that exists in space and time. To ask what lies beyond may be akin to asking what lies north of the North Pole or west of the westernmost horizon. Perhaps there is nothing. Perhaps there are other realms, other universes, existing in ways our senses and instruments cannot perceive. The expansion itself provides no clues, only evidence that our familiar notions of boundary, edge, and limit are inadequate. It is a philosophical shock as much as a scientific one. The cosmos does not merely challenge measurement, it challenges the mind. The implications of faster-than-light recession deepen the mystery. When we look to the most distant galaxies, we are peering into regions of space that are fundamentally unreachable, regions from which no signal will ever return. Light emitted billions of years ago is stretched, diluted, carried on the expanding fabric so that the objects themselves recede ever faster. There exists a cosmic horizon, a boundary defined not by any material edge, but by the limits of communication, the edge of what can be observed. Beyond that horizon, the universe continues, but its contents are forever inaccessible. The expansion of space has thus created an isolation that is as profound as it is invisible, a separation that challenges our understanding of proximity, distance, and cosmic kinship. Einstein's initial resistance, in this light, becomes understandable. General relativity predicted a dynamic universe, yet the human mind struggles with the abstraction of space itself moving. Classical mechanics, grounded in the motion of objects through fixed space, offered no guide for this reality. Even today, the notion that space-time can stretch, that distances can grow while the fabric itself carries the motion, remains unsettling. It is a cosmic paradox: motion without traversing, speed without travel, expansion without exterior. The universe moves, yet it has nowhere to go. It grows, yet it has no edge into which it may expand. It is an infinite dance without a ballroom, a tide rising into emptiness, a painting unrolling into oblivion. The psychological shock was compounded by the evidence of uniformity. Observers everywhere would see the same expansion, the same recession of galaxies, suggesting that the stretching of space is not local, not preferential, not centered around any one point. The universe is homogeneous and isotropic on large scales, a principle that renders our traditional metaphors of containers, boundaries, and edges obsolete. No vantage is central, no perspective privileged. Each observer finds themselves at the apparent center of expansion, yet this center is an illusion, a byproduct of every point moving away from every other. The cosmos defies conventional geometry, requiring instead a language of curvature, metric expansion, and four-dimensional space that challenges intuition and comforts only with mathematical elegance. The human mind, accustomed to walls and horizons, struggles with such abstraction. Philosophers and cosmologists alike have noted the existential weight of this realization. The universe is not bounded, yet it moves. It is finite in history, with a beginning in time, yet infinite in its unfolding. Our notions of containment, exterior, and beyond are inadequate, leaving only speculation to bridge the gap between observation and understanding. This is a realm where mathematics guides imagination, where spectral lines and redshifts hint at truths that cannot be touched, where the very fabric of reality defies sensory perception. The expansion of space also reshapes our understanding of causality. Regions separated by vast distances recede from each other so rapidly that no signal, no photon, no particle can traverse the expanding gulf. These regions are causally disconnected, forming horizons beyond which information is forever lost. The universe is simultaneously interconnected and isolated, a paradox that challenges not only physics but philosophy. Each galaxy moves away from its neighbors, yet all follow the same underlying rhythm, a cosmic choreography dictated by the unseen energy that drives expansion. Dark energy, though invisible and mysterious, exerts its influence uniformly, pushing the fabric of space outward, creating a reality in which motion and distance are inseparable from the structure of space-time itself. Even the term space itself stretching is a simplification. The mathematics of general relativity describe this expansion not as motion through a void, but as a change in the distances defined by the metric of space-time. Galaxies are carried along not because they are moving in the conventional sense, but because the intervals between them increase. This distinction is subtle yet profound. It is the difference between swimming through a river and watching the river itself lengthen beneath one's feet. The velocities observed are not velocities in space, they are velocities of space. And this is where the paradox pierces the mind. The universe expands, yet it has no outside, no container, no external frame of reference. Its growth is absolute, measured only against itself. As scientists struggled to reconcile these concepts, the broader philosophical implications emerged. The universe, once a finite and static backdrop for celestial drama, is revealed as a dynamic, unbounded continuum. The question of what lies beyond becomes not merely a scientific query, but a meditation on the limits of perception, the boundaries of reason, and the human longing for edges in an edgeless reality. If nothing exists beyond, then expansion is self-referential, a stretching into infinity. If something does exist, it remains invisible, inaccessible, beyond the horizon of observation and understanding. Either possibility confronts humanity with the vastness of the unknown. The shock is not merely intellectual but emotional. It alters the way we envision our place in the cosmos. Earth is not the center of a container. Humanity is not the privileged witness to a finite theater. We inhabit a fabric that stretches silently and relentlessly, a stage that grows beyond our comprehension. The very notion of expansion challenges the comforting narratives of control and containment, inviting instead humility, wonder, and awe. Each redshift measured, each distant galaxy catalogued, is a reminder of the inexorable motion of space, a motion that has been unfolding for billions of years, indifferent to observers, yet comprehensible through the language of physics. In this paradox lies a profound mystery. The universe grows, yet it stretches into nothing that can be perceived. The faster-than-light recession of distant galaxies, the dissolution of classical notions of motion, and the absence of a cosmic edge converge into a singular realization. Our intuition, evolved to navigate a terrestrial world, is insufficient to grasp the cosmic truth. The universe is a dynamic, unbounded expanse, and its expansion is a phenomenon both measurable and incomprehensible. To study it is to confront limits of understanding, to measure reality while standing at the edge of the unknowable. And yet, in this shock, there is beauty. The universe reveals its motions not with violence, but with quiet elegance, a rhythm traced across billions of light years. Galaxies drift apart in a dance that obeys the deep laws of space-time. Light stretches, time unfolds, and the cosmos continues, expanding into a realm that may forever elude perception. The scientific shock, while disorienting, is also a doorway, a gateway into deeper questions about reality, about the meaning of space and time, and about the very nature of existence. In the wake of discovery, scientists continue to measure, to theorize, to model the expansion with ever-increasing precision. Yet the paradox remains. Space stretches, galaxies recede, and the universe grows into a realm that may be beyond imagining. The shock experienced by Einstein, by Hubble, by Friedman, and Lemaitre persists today. It is the shock of confronting a cosmos that moves not within space, but through the space that is itself expanding, stretching, breathing, a universe alive with motion, yet without edge, without beyond, a paradox that challenges the mind, humbles the imagination, and evokes a profound sense of awe. After the initial revelation that the cosmos was not static but expanding, the scientific journey entered a phase of meticulous observation, of instruments attuned to the faintest whispers of the universe's origin. The discovery of motion alone was not enough. The universe demanded to be measured, mapped, and understood in the full richness of its scale. In 1964, Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, stumbled upon a faint, persistent hum in their radio antenna, a noise that defied all terrestrial explanation. It was isotropic, uniform across the sky, a whisper of light that had traveled for nearly 14 billion years. This was the cosmic microwave background, the echo of the universe's infancy, a relic of the primordial fireball from which all matter and energy emerged. The CMB was more than a static signal. It was a window into the earliest moments of cosmic history. Its uniformity revealed that expansion had been pervasive and consistent from the beginning, a smooth stretching of space-time itself. Minute variations in its temperature, mapped with increasing precision by instruments such as the Cosmic Background Explorer, COBE, WMAP, and later Planck, trace the subtle seeds of structure, the nascent clumps of matter that would eventually coalesce into galaxies, clusters, and the vast cosmic web. Through these observations, scientists could see the universe as a living tapestry, one shaped not by chance alone, but by the deep interplay of matter, energy, and the metric of space-time. The tools of observation grew ever more sophisticated. The Hubble Space Telescope, peering across billions of light years, revealed galaxies in astonishing detail, including those so distant that their light had traveled nearly the age of the universe to reach us. Deep field surveys captured swaths of space teeming with faint galaxies, each one a monument to the inexorable expansion traced by Hubble decades earlier. Spectroscopy allowed precise measurement of redshifts, revealing velocities and distances with ever finer resolution. Through these instruments, the expansion of the universe was no longer a theory, but a continuously observable reality, its effects written across the night sky. Yet the cosmos held further surprises. In the late 1990s, two independent teams of astronomers, observing distant Type Ia supernovae, uncovered a revelation that deepened the mystery of cosmic expansion. These stellar explosions, remarkably uniform in their intrinsic brightness, serve as cosmic mileposts, allowing the measurement of distances across the universe. The data revealed that the rate of expansion was not slowing under gravity, as had been expected, but accelerating. A subtle repulsive influence permeated space, counteracting gravity's pull and stretching the cosmos ever faster. This invisible agent, which came to be called dark energy, constitutes roughly 70% of the universe's total energy content. Yet its nature remains elusive, a phantom embedded in the very fabric of space. The discovery of acceleration reframed every prior understanding. Expansion was no longer a passive unfolding, but a dynamic process, driven by forces beyond direct perception. Dark energy acts uniformly, invisible yet pervasive, a reminder that the universe contains realities that cannot be seen with the eye, only inferred from their gravitational and kinematic footprints. The CMB, the redshift of distant galaxies, the behavior of supernovae, all converge to tell a consistent story. Space itself is stretching, accelerating, and shaping the evolution of matter and light in ways that challenge intuition. Mathematical models rooted in general relativity provide the framework to interpret these observations. Einstein's equations describe a universe in which the geometry of space-time itself dictates motion, a cosmos that can expand without requiring an external medium into which to grow. Space is not a substance floating within some greater void. It is the stage, the fabric, the entirety of physical reality, capable of stretching, bending, and curving under the influence of matter and energy. Solutions to these equations allow for universes that are flat, open, or closed, finite yet unbounded, infinite yet measurable. The very notion of beyond becomes a question of geometry rather than a physical frontier, a challenge that merges physics with the philosophical contemplation of infinity. Beyond the equations, the universe's structure offers further insight. On the largest scales, galaxies are not distributed randomly, but form a vast cosmic web, an intricate lattice of filaments, clusters, and voids. These patterns are relics of initial density fluctuations amplified by gravity, imprinted upon space as it expanded. Filaments stretch across hundreds of millions of light years, linking clusters of galaxies, while enormous voids, regions largely devoid of matter, punctuate the cosmic landscape. The distribution of these structures traces the influence of expansion, the subtle hand of dark energy, and the gravitational scaffolding underlying the observable universe. By mapping this large-scale structure, cosmologists discern the rhythm of cosmic growth, the interplay between matter, energy, and the geometry of space itself. Each observation reinforces the paradoxical nature of expansion. The farther a galaxy lies, the faster it recedes, a relationship encoded in Hubble's law and refined with ever greater precision. The acceleration measured in type Ia supernovae reveals that the stretching of space is not uniform in time, but dynamic, increasing as dark energy exerts its influence. The cosmic web, born of tiny quantum fluctuations amplified during inflation, provides a three-dimensional map of expansion's history, a fossil record of the forces shaping space-time. The universe is not merely stretching. It is a structured, evolving entity, its growth inscribed in light, matter, and the subtle glow of relic radiation. Speculation, grounded in these observations, offers glimpses into possibilities beyond direct measurement. The accelerated expansion suggests that vast regions of space may eventually move beyond our observable horizon, their light unable to reach future observers. In such a scenario, galaxies, clusters, and filaments may fade into a lonely darkness, leaving a universe that appears increasingly empty despite its underlying structure. Models of inflation posit that the early universe underwent an even more rapid expansion, smoothing space and embedding the initial conditions for the cosmic microwave background we observe today. These insights hint at processes that act on scales beyond human experience, where the behavior of space itself dominates the evolution of reality. The interplay between theory and observation continues to deepen our understanding. Instruments such as Planck, WMAP, and the Hubble Space Telescope provide data with unprecedented precision, allowing cosmologists to test models of dark energy, inflation, and large-scale structure. Simulations of cosmic evolution performed on supercomputers recreate the formation of filaments, voids, and clusters under the influence of expansion and gravity. These virtual universes mirror observations with remarkable fidelity, reinforcing the connection between mathematical abstraction and physical reality. Yet each success uncovers further questions. What is the nature of dark energy? Why does it dominate the universe at this epoch? And what does it imply about the ultimate fate of cosmic expansion? The deeper investigation also highlights the interconnectedness of scales. The stretching of space is apparent across billions of light years, yet its effects are encoded in the minute anisotropies of the CMB. The motion of individual galaxies, the clustering of matter, and the brightness of distant supernovae all provide pieces of a puzzle that spans the entirety of observable reality. Each measurement, each spectral line, each temperature fluctuation is a note in the symphony of cosmic expansion, resonating across time and space. The universe speaks in patterns, and through careful observation, scientists begin to interpret its subtle language. Philosophically, this phase of investigation evokes a profound sense of awe. The universe is at once comprehensible and mysterious, its expansion observable yet conceptually elusive. Instruments reveal structure and motion, yet the underlying cause, the properties of dark energy, the geometry of space, the inflationary epoch, remains partially hidden. Humanity perceives only a fraction of what exists, yet within that fraction lies a story of origins, growth, and the dynamic unfolding of reality. The expansion of space is not merely a scientific phenomenon. It is a lens through which to contemplate existence itself, the passage of time, and the interwoven nature of matter, energy, and geometry. Each discovery in this phase is both confirmation and revelation. The CMB confirms the Big Bang, the uniformity of expansion, and the seeds of structure. The deep field observations trace galaxies across the breadth of cosmic time. The accelerating expansion reveals the dominance of dark energy. Mathematical models illustrate how space can grow without a surrounding medium, while the cosmic web maps the distribution of matter across unimaginable distances. Together, these strands weave a portrait of a universe that is vast, dynamic, and profoundly ordered, yet filled with enigmas that challenge intuition. In the silent patterns of the cosmic microwave background, in the faint light of distant galaxies, in the accelerating recession measured by supernovae, the universe speaks of its own expansion. The fabric of space stretches, carrying galaxies, clusters, and filaments along paths defined by the interplay of matter, energy, and geometry. Each observation adds depth to the mystery. Each measurement refines our understanding, Yet the ultimate questions remain. Why does space expand? What governs its acceleration? And into what, if anything, does it extend? This phase of investigation is a testament to the union of patience, ingenuity, and curiosity. From the serendipitous discovery of the CMB by Penzias and Wilson, to the high-precision mapping by Planck and WMAP, to the deep-field imaging of Hubble, humanity has constructed a detailed portrait of an expanding cosmos. Yet the universe remains more than the sum of observations. Its acceleration, the vast cosmic web, the pervading dark energy, all point toward mysteries beyond direct perception, phenomena that challenge understanding while inspiring wonder. The deeper investigation confirms a paradox. The universe is both measurable and unknowable, structured and infinite in its unfolding. Space stretches without edge, expands without container, and carries its contents along paths dictated by the subtle interplay of physical laws. The cosmic web traces the footprints of early fluctuations, while dark energy drives acceleration on scales beyond comprehension. The CMB whispers of origins, and the light of distant galaxies chronicles billions of years of motion. Expansion is no longer merely observed, it is mapped, calculated, and traced, yet it continues to defy intuition, leaving the mind suspended between comprehension and awe. In this way, the universe reveals itself slowly, layer by layer. Each observation in the deeper investigation, CMB mapping, deep field imaging, supernova measurements, large-scale structure surveys, peels back a veil, revealing a cosmos in motion, growing and evolving across space and time. Yet, with each revelation comes the persistent reminder that space itself stretches into the unknown, and the ultimate nature of this expansion, and the reality beyond what can be observed, remains an open question, one that invites both scientific inquiry and philosophical reflection. Through the instruments of observation and the language of mathematics, humanity glimpses the elegance of cosmic expansion. Yet the mystery persists, growing deeper as the universe itself grows, its fabric stretching across billions of light years, carrying galaxies along silent paths into a future that is measured but unknown, mapped but still shrouded in the profound enigma of space itself. As the universe reveals itself through the lenses of ever more precise instruments, the quiet revelation of expansion evolves into a phenomenon both mesmerizing and disquieting. The galaxies, once thought fixed upon the cosmic stage, are carried outward by the very fabric of space itself, and over immense distances, their recession exceeds the speed of light. This is not motion through space, which relativity forbids, but a stretching of space itself, a subtle, imperceptible lengthening that accumulates across billions of light years. The farther a galaxy lies, the swifter its departure, slipping beyond the reach of observation, receding into a region forever inaccessible. The expansion is accelerating, driven by the mysterious agent known as dark energy, and with it comes a conceptual leap so profound that the human mind struggles to comprehend it. The universe is growing faster than light, and its limits may never be touched. This acceleration introduces the horizon problem, a puzzle that deepens the mystery. Distant regions of space are separated by such vast distances that light from one could not have reached the other since the birth of the universe. How then could these regions, causally disconnected, exhibit the remarkable uniformity observed in the cosmic microwave background? Temperatures across billions of light years are nearly identical, a whisper of coherence that seems impossible under ordinary assumptions. The universe appears to communicate across impossibly vast scales, revealing order where, by conventional logic, none should exist. This tension between observation and expectation hints at processes far beyond the comprehension of everyday experience, a hint of an underlying architecture in the cosmic fabric that extends beyond the visible. The concept of cosmic inflation provides a compelling framework for this enigma. In the first fractions of a second after the Big Bang, the universe is theorized to have expanded exponentially, growing by factors so immense that the scale of space itself was multiplied unimaginably in a brief instant. Inflation smoothed and stretched the primordial energy, embedding the initial uniformity that persists in the cosmic microwave background. Tiny quantum fluctuations, magnified by this expansion, became the seeds of galaxies, clusters, and the cosmic web. Inflation, in its elegance and audacity, resolves the horizon problem, yet it carries with it an unsettling implication. The universe may be far vaster than anything that can be observed, a realm that dwarfs the human imagination, and eludes direct perception. Beyond inflation lies a landscape of speculative yet scientifically grounded possibilities. Space may be infinite, extending without limit in all directions, carrying galaxies and dark energy into an endless expanse. It may be cyclic, contracting and expanding in successive eons, each epoch giving rise to a new cosmic chapter. Or it may be finite yet unbounded, a four-dimensional hypersphere in which the universe loops back upon itself, without edge, without center, without outside. Each scenario challenges not only measurement, but intuition, defying the spatial metaphors that have guided human understanding for millennia. To confront these possibilities is to confront the limits of cognition, to recognize that the universe may be fundamentally unknowable in its totality. The accelerating expansion and inflationary history together create a profound sense of isolation. The universe is not merely vast, it is disconnected. There exist regions beyond our cosmic horizon, regions whose light has not yet, and may never, reach our instruments. Some galaxies that once emitted light visible to distant observers are now receding faster than that light can travel. The observable universe, immense though it is, may constitute only a small fraction of the total reality. Beyond the horizon lies uncertainty, a realm of potential infinity that may forever elude perception. The universe, in its grandeur, may be isolated in a boundless expanse, and humanity's gaze, no matter how powerful, can touch only the local stretch of space-time that falls within causal contact. Mathematics provides a way to navigate these conceptual frontiers. General relativity permits the metric of space-time to evolve independently, allowing regions to recede faster than light while preserving the local laws of physics. The equations describe a cosmos that can be finite and unbounded, curved into a higher dimensional geometry that lacks edges yet remains measurable. Inflationary models suggest a multiverse, a collection of universes born from quantum fluctuations, each potentially with its own expansion, laws, and dimensions. These frameworks stretch the imagination, demanding a shift from the ordinary notions of space as container to space as dynamic, malleable, and potentially infinite. Observational evidence continues to reinforce the magnitude of this cosmic acceleration. Type Ia supernovae reveal the expansion's growth over time, mapping the influence of dark energy across billions of years. The large-scale structure, the cosmic web of filaments and voids, traces the imprint of inflationary fluctuations stretched by expansion. Surveys like the Sloan Digital Sky Survey chart galaxies across the observable universe, revealing the statistical uniformity and clustering that betray both the ancient origins and the ongoing stretching of space. Even as data accumulate, the conceptual gulf between observation and human intuition widens. Space itself is not a void to traverse, but a canvas that stretches, grows, and isolates, carrying the contents of the cosmos along paths dictated by its own geometry. The acceleration implies a future in which regions of the cosmos disappear from view. Galaxies once visible will cross the horizon, receding at speeds that prevent light from ever reaching future observers. The observable universe will shrink not in size but in accessibility, leaving only local structures, the Milky Way and its immediate neighbors, as islands in a darkening sea. The distant cosmos, rich with history and structure, will vanish from observation, its light trapped beyond the expansion. This paints a picture of a universe simultaneously full and empty, connected in the past yet destined to fragment in perception, emphasizing the paradoxical nature of space itself. Speculative models further amplify the mystery. If the universe is infinite, acceleration stretches it endlessly, and the totality of space is beyond counting or measurement. If it is cyclic, each contraction and expansion may reset the observable horizon, erasing traces of previous epochs while leaving the laws of physics intact. If finite yet unbounded, the universe is a closed geometry, a cosmic loop with no edge, in which motion through space follows curved trajectories. And every journey eventually returns to its origin, though the scale renders this nearly impossible to experience. Each scenario is consistent with observed expansion yet challenges human perception, demanding the acceptance of realities that are simultaneously measurable and conceptually alien. The emotional tension in confronting these possibilities is profound. Humanity stands on a small planet, within a galaxy carried along by space itself, in a universe that stretches far beyond comprehension. The The acceleration of expansion and the isolation of cosmic regions evoke a sense of cosmic solitude, an awareness that observation is limited, understanding is partial, and the totality may remain forever beyond reach. Philosophers, cosmologists, and physicists alike grapple with this tension. The universe is intimate in its observable details, yet immense in ways that defy complete perception. The accelerating expansion is both revelation and admonition, a reminder of the scale and grandeur of reality and of the limits imposed upon sentient observers. In practical terms, the horizon problem, inflation, and acceleration converge to suggest a universe that is dynamic, isolated, and almost unfathomably vast. The cosmic microwave background, observed with exquisite precision by Planck and WMAP, preserves a memory of the early uniformity that inflation smoothed. Yet beyond that observable shell may lie a cosmos entirely unseen, galaxies receding faster than light, filaments stretching across hundreds of millions of light years, voids of incomprehensible scale. All these structures are the observable manifestation of forces acting on an unimaginable canvas. The universe is expanding not into emptiness, but through a domain whose totality remains undefined, a realm where conventional ideas of edge, exterior, and beyond dissolve. The conceptual leap required to fully grasp these dynamics is immense. Space itself grows, carrying all within it, and yet it has no outside into which it expands. The universe may be infinite, or cyclic, or finite, yet unbounded, a four-dimensional hypersphere in which the familiar notions of center and edge are meaningless. Regions of space remain causally disconnected, yet the large-scale uniformity persists, suggesting a coherence that is embedded in the very physics of inflation and expansion. Observational instruments reveal only part of this vast reality, and theoretical frameworks extend imagination into the unobservable, offering models that challenge intuition while remaining consistent with empirical data. In the face of these revelations, the human mind encounters both awe and unease. The universe is at once knowable through mathematics, observation, and simulation, and unknowable in its totality, extending beyond the horizon of perception. Expansion, acceleration, and inflation combine to create a cosmos that is profoundly dynamic, structured, yet mysterious, isolated, yet connected. The accelerating universe suggests a future in which the observable cosmos shrinks, leaving only local structures while vast regions recede beyond reach, reminding us that knowledge is always partial, and perception is bounded by the limits of light and space. The universe's acceleration, its inflationary past, and its potential geometric forms converge to emphasize the profundity of cosmic mystery. Space stretches faster than light, carrying galaxies and structures beyond the reach of observation. Regions remain causally disconnected, yet uniformly ordered, hinting at the subtle coherence of physics across unimaginable scales. The universe may be infinite, cyclic, or finite yet unbounded, expanding in a manner that eludes direct perception. Humanity, poised within this vast expanse, perceives only a fraction of reality, yet through observation and mathematics, glimpses the larger narrative of expansion, growth, and cosmic isolation. In the end, the escalation of cosmic expansion transforms the initial discovery of motion into a panorama of mystery. Space itself stretches and accelerates, carrying galaxies, clusters, and filaments along paths dictated by the geometry of space-time. Inflation reveals the universe's earliest moments, smoothing space and embedding the seeds of structure. Dark energy drives acceleration, creating a future in which the observable cosmos will diminish as distant galaxies recede beyond reach. And in contemplating the infinite possibilities, hyperspherical geometry, cyclic cosmology, or unbounded infinity, the human mind confronts the ultimate challenge: to imagine a universe without edge, without center, and without outside. A cosmos both measurable and unknowable, magnificent and profoundly isolating. In the quiet spaces between observation and understanding, science ventures into speculation, guided by mathematics, constrained by evidence, yet unafraid to contemplate the unimaginable. The expansion of the universe is no longer merely measured. It demands explanation. What drives the fabric of space to stretch? Into what, if anything, does it expand? And might the reality we observe be but a fragment of a far grander, more complex cosmic tapestry? These questions have inspired some of the most profound and daring theories in modern cosmology, each one offering a lens through which to interpret the enigma of an ever-expanding universe. Among the most striking is the idea of a multiverse. In this framework, our universe is but a single bubble in a vast, possibly infinite foam of universes, each with its own laws of physics, constants, and dimensions. The inflationary epoch, which stretched space in the first fractions of a second after the Big Bang, may have given rise to countless other bubbles, forming a cosmic landscape beyond our observable horizon. Each universe might evolve independently, disconnected yet part of a broader ensemble. If true, the multiverse renders the concept of beyond simultaneously trivial and profound. Beyond our observable cosmos, countless other realities may exist, unreachable yet intimately linked through the shared physics of creation. The notion challenges not only measurement but imagination, requiring a shift from thinking of the universe as singular and absolute to considering it as a localized manifestation of a deeper, more complex reality. Equally compelling are theories that invoke higher dimensional spaces. String theory, for example, posits that the fundamental constituents of reality are one-dimensional strings vibrating across multiple dimensions, beyond the familiar three of space and one of time. In some formulations, our universe exists as a brain, a three-dimensional membrane embedded in a higher dimensional bulk. Expansion, in this view, might occur not merely within observable dimensions, but along directions imperceptible to human senses. Galaxies recede not only through three-dimensional space, but within a multidimensional framework, their motion shaped by forces that operate beyond perception. Such models allow for possibilities that seem surreal: parallel brains influencing one another, gravity leaking into extra dimensions, or collisions between brains igniting new epochs of expansion. Here, speculation and observation intersect. As higher dimensional physics provides explanations for dark energy, the uniformity of expansion, and the large-scale structure of the cosmos, the influence of quantum vacuum energy offers another avenue of understanding. Empty space, far from being a void, seethes with fluctuations at the quantum level, ephemeral particles appearing and vanishing in accordance with the uncertainty principle. These fluctuations produce a vacuum energy, a subtle but pervasive pressure that pushes space outward. Dark energy, the mysterious force driving the acceleration of cosmic expansion, may be a macroscopic manifestation of this quantum phenomenon. Unlike matter or radiation, vacuum energy exerts uniform pressure, stretching the fabric of space itself. Its effect is imperceptible locally but profound across cosmological scales, shaping the destiny of the universe and framing the ultimate question. The universe grows because space itself possesses energy, a silent dynamism embedded in the fabric of existence. Cosmologists also explore the geometry of space as a means to understand expansion and the elusive beyond. 3. Primary models describe the universe's large-scale structure, closed, flat, and open. In a closed universe, space curves back upon itself, finite yet unbounded, like the surface of a four-dimensional sphere. In a flat universe, space is infinite and Euclidean, extending endlessly in all directions. In an open universe, space is negatively curved, hyperbolic and potentially infinite, expanding without bound. Each geometry carries profound implications. A closed cosmos has no exterior. Moving in a straight line long enough eventually returns one to the starting point. A flat or open universe may truly be infinite, a domain without edge or limit. These models allow scientists to explore scenarios in which the observable universe is only a small fraction of a vaster reality, and in which traditional notions of interior and exterior, center and periphery, lose their meaning. Thought experiments help to anchor these abstract concepts in intuition. The balloon analogy, often used to visualize expansion, imagines galaxies as dots on the surface of a balloon. As the balloon inflates, the dots move away from one another, not by traversing the surface, but because the surface itself grows. There is no center on the surface, no edge into which it expands. The motion is intrinsic to the geometry. Similarly, projecting the universe onto a hypersphere illustrates the notion of finite yet unbounded space, where the interior is inseparable from the surface and the exterior does not exist. These analogies, while imperfect, provide a bridge between the human mind's spatial intuition and the counterintuitive reality of cosmic expansion, a way to grasp infinity and unboundedness through metaphor. Philosophical reflection emerges naturally from these theories. If the universe is finite, one is compelled to ask, finite in what sense and finite relative to what? What does it mean for space to have an interior without exterior, for the cosmos to be bounded yet without edge? If the universe is infinite, what does infinity signify in physical terms? Does it correspond to an unending expanse of matter and energy, or is it a conceptual limit beyond which measurement cannot reach? Each speculation carries emotional weight as well as intellectual challenge. The universe is not simply a backdrop for life and observation. It is an active participant in the unfolding of reality, stretching, curving, and evolving in ways that transcend human scale and perception. Speculative thought experiments extend even further into the interplay between quantum mechanics and cosmology. Inflation, driven by energy fields, may generate new universes through quantum tunneling, forming regions where space inflates independently, beyond the causal reach of our observable cosmos. The multiverse may therefore be dynamic, a perpetually unfolding ensemble of universes, each expanding according to its own physical laws. Higher dimensional frameworks allow for brane collisions, which could ignite Big Bang-like events, seeding new universes with the same or entirely different physical properties. These ideas, though speculative, are grounded in equations derived from general relativity and quantum field theory, demonstrating that imagination guided by mathematics can extend our understanding to realms that cannot yet be observed. Debates within the scientific community reflect both rigor and humility. While multiverse scenarios intrigue theorists, empirical validation remains challenging, limited by the constraints of observation. Higher dimensional models provide elegant explanations for dark energy and unification, yet they predict phenomena at scales beyond current experimental reach. The precise nature of vacuum energy, its relationship to dark energy, and its role in cosmic acceleration remains uncertain, a puzzle whose resolution may require new physics. The geometry of space, whether closed, flat, or open, is constrained by measurements of the cosmic microwave background, yet subtle deviations could reveal deeper truths about the universe's shape and fate. These debates maintain emotional gravity because they underscore the limits of knowledge, even as they illuminate possibilities. Each theoretical framework carries its own philosophical resonance. The multiverse evokes a sense of cosmic humility. The observable universe may be only a local realization among countless others, reminding humanity that reality may be vastly richer than perception alone suggests. Higher dimensional spaces hint at unseen structures and forces, emphasizing that the familiar four dimensions of experience may be only a shadow of a deeper, multidimensional reality. Quantum vacuum energy suggests that even empty space is alive with potential, a reservoir of dynamism that shapes the growth of the cosmos. Geometry challenges perception itself, showing that infinity, closure, and curvature are not abstract mathematical curiosities, but fundamental properties of the stage on which existence unfolds. Analogies serve as a compass in this landscape of speculation. The balloon and hypersphere metaphors allow the mind to explore finite, yet unbounded space, providing intuitive insight into concepts that are otherwise almost impossible to visualize. The multiverse can be imagined as a froth of bubbles, each universe isolated yet forming a collective ensemble, a cosmic network beyond direct perception. Higher dimensions, though invisible, can be approached through projections, mathematical mappings, and physical consequences that manifest in observable phenomena such as gravitational waves, particle interactions, or subtle curvature of space. These mental models are not mere exercises. They are essential tools in bridging the gap between theory and comprehension. In contemplating these possibilities, one cannot avoid the emotional impact. The universe, in its expansion, in its acceleration, and in the speculative frameworks that seek to explain it, evokes awe, humility, and profound reflection. The cosmos is simultaneously knowable and unknowable, structured yet mysterious, accessible through observation yet extending into realms beyond direct perception. Each theory, whether multiverse, higher dimensions, quantum vacuum energy, or geometric curvature, offers a glimpse into the vastness and subtlety of reality, while reminding humanity of the limitations inherent in perception and cognition. Yet speculation does not diminish rigor. Cosmologists seek constraints, predictions, and connections to observation. Measurements of the cosmic microwave background constrain curvature and geometry. Surveys of galaxy distribution and supernova brightness inform models of expansion and dark energy. Particle physics experiments explore the nature of vacuum energy and the potential existence of extra dimensions. Each speculation is tethered to reality, grounded in mathematics, observation, or theoretical consistency. It is a delicate balance, to imagine boldly while remaining anchored in empirical truth. Ultimately, the universe as observed and theorized is a realm of both certainty and mystery. Expansion is measurable, acceleration is observed, the cosmic microwave background preserves a record of origins, and large-scale structure maps the cosmic web. Yet the interpretation of what lies beyond, whether multiverse, higher dimensions, or infinite space, remains a profound challenge. Thought experiments, analogies, and speculative frameworks offer pathways to understanding, but the ultimate nature of the universe, its totality, and the meaning of beyond may elude definitive perception. In this convergence of observation, theory, and speculation, the mind confronts both scale and subtlety. The universe grows, stretches, and evolves. In the quietude of observation, where light from billions of years past reaches fragile detectors, humanity has constructed instruments capable of measuring the heartbeat of the cosmos. These are not mere telescopes, but portals into the ancient universe, devices designed to read the subtle language of photons and gravitational waves, to trace the expansion of space and the influence of forces unseen. The James Webb Space Telescope, with its gold-coated mirrors and infrared gaze, peers through cosmic dust and time, revealing galaxies forming in the universe's infancy, their light stretched by eons of expansion. Every photon carries a whisper of history, a clue to the rate at which space itself has grown, a measure of the acceleration that shapes the cosmos. Alongside Webb, the Vera Rubin Observatory sweeps across the sky with panoramic precision, surveying billions of galaxies in an effort to map the architecture of the cosmos. It captures the subtle motions of galaxies, the patterns of clustering, the gravitational fingerprints that reveal dark matter's hidden hand. Euclid, the European Space Agency's ambitious mission, observes the large-scale distribution of galaxies and the cosmic web, probing the influence of dark energy on the expansion of space. These instruments, diverse in method yet unified in purpose, construct a multidimensional portrait of a universe in motion, an accelerating expanse whose very fabric is shaped by forces yet only partially understood. Measurement is both an art and a science. Redshift surveys capture the stretching of light from distant galaxies, the Doppler shift that encodes their velocity away from us. The cosmic distance ladder, built of Cepheid variables, supernovae, and standard candles, allows astronomers to calibrate distances across immense scales. Baryon acoustic oscillations, subtle ripples imprinted in the distribution of matter, offer a ruler across cosmic epochs, linking observations to models of expansion with exquisite precision. Each of these methods independently confirms the universe's acceleration, yet each also hints at unresolved tensions. The precise value of the Hubble constant, the rate of expansion today, appears to differ depending on measurement, a subtle discord that may point to new physics or hidden complexity. The pursuit of dark energy, the enigmatic force driving acceleration, is central to these observational efforts. Cosmologists seek not only to measure its effects, but to characterize its properties, whether it is truly constant or dynamic, evolving over time. Every deviation in the Hubble constant, every subtle anomaly in large-scale structure, is a potential clue, a possible crack in the framework of established cosmology. Observatories record light from distant supernova, map galaxy clusters, and trace cosmic filaments, seeking correlations that may reveal dark energy's nature. Yet each discovery deepens the mystery, for the very phenomenon that drives the universe outward remains imperceptible in isolation, manifest only through its influence on space and matter. Gravitational wave detectors add a new dimension to this exploration. LIGO and Virgo, instruments of exquisite sensitivity, measure ripples in space-time itself, caused by merging black holes and neutron stars. These waves carry information not only about their violent origins, but about the structure of space-time across vast distances. In principle, gravitational waves offer a complementary method for measuring cosmic expansion, an independent probe of the Hubble constant and the growth of structure. As detectors improve, they may reveal subtle features of space itself, the dynamic geometry through which galaxies drift, and perhaps hints of phenomena that remain hidden to light alone. Supercomputer simulations augment observational tools, turning raw data into virtual universes. Cosmologists feed initial conditions derived from the cosmic microwave background into models governed by general relativity, dark matter, and dark energy. Across millions of computing hours, these simulations trace the evolution of galaxies, clusters, filaments, and voids, predicting the emergence of the cosmic web and its future unfolding. They allow scientists to test hypotheses, to compare the growth of structure under different assumptions about dark energy or geometry. Through these digital reconstructions, the invisible becomes observable, the abstract tangible, and the universe reveals patterns that guide theory, even when direct observation is impossible. Yet the greatest tension lies in the fundamental nature of the question itself. What exists beyond the universe? All instruments, no matter how precise, observe only within the cosmic horizon, the limit set by the speed of light and the age of the cosmos. Beyond this boundary, space may continue endlessly, may fold back upon itself, or may form one of the hypothetical multiverse domains predicted by inflationary theory. But these realms, by definition, are unobservable, inaccessible to direct measurement. Cosmology, for all its precision and rigor, confronts the boundary between the measurable and the unknowable, reminding us that some questions, though scientifically motivated, may remain forever beyond empirical reach. The interplay between observation and speculation is delicate. Every redshift catalogue, every supernova survey, every gravitational wave detection constrains the possible, narrows the field of models, and deepens understanding. Yet simultaneously, the same observations expose the universe's vastness and the limits of perception. The accelerating expansion, measured through countless instruments, implies a cosmos in which distant galaxies slip beyond reach, where the observable universe is only a fragment of a greater whole. Simulations reveal patterns and growth, but the ultimate canvas, the totality of space, the beyond, remains inaccessible. Philosophically, these endeavors reflect the human impulse to know, even in the face of limits. Instruments extend perception across space and time, bridging billions of light years, yet they confront an inherent boundary. The universe is observable only to a finite horizon, a shell of light and matter from which information has arrived. Beyond, the cosmos may continue infinitely or terminate in ways that defy intuition. Cosmologists build mathematical models to extrapolate, to project the unknown from the known, yet always with the awareness that these models are approximations, interpretations tethered to what can be measured. In this tension lies both challenge and poetry, the recognition that observation illuminates but does not exhaust the mystery. Every program in modern cosmology contributes a piece to this puzzle. James Webb peers into the infrared, capturing ancient galaxies and the earliest star formation. The Vera Rubin Observatory maps motions across billions of galaxies, revealing subtle gravitational influences. Euclid surveys the large-scale structure and the effects of dark energy, linking observations across cosmic time. Gravitational wave detectors measure ripples in space-time itself, confirming general relativity and probing the expansion of the universe in new ways. Supercomputer simulations turn these data into virtual universes, allowing scientists to test models and predict the unfolding of structure. Together they form a tapestry of tools, each strand complementing the other, each revealing both knowledge and limitation. Despite these advances, the philosophical tension endures. Space expands faster than light over immense distances, carrying galaxies beyond observational reach. Dark energy drives acceleration, its nature inferred only indirectly. Cosmic horizons define the boundary of perception, isolating the observable from the unobservable. Simulations extend imagination, yet the universe outside the horizon remains unknowable, a domain where speculation is necessary but observation is impossible. Humanity stands within the observable shell, equipped with instruments that decode light, gravity, and structure. Yet the ultimate question, what lies beyond the universe, remains suspended, a silent challenge at the edge of perception. The refinement of measurements itself exemplifies this duality. Efforts to resolve the Hubble tension, the discrepancy between the local and early universe measurements of expansion, highlight the subtlety of cosmic inquiry. Observations from supernovae, Cepheid variables, and the cosmic microwave background yield slightly divergent results, suggesting either unknown systematic errors or new physics. Every refinement sharpens knowledge, yet simultaneously hints at the incompleteness of understanding. The cosmos, in accelerating expansion and vast scale, resists full comprehension, reminding scientists that discovery is a journey punctuated by deeper questions. Simulations of cosmic evolution reveal not only the universe's past, but also its potential future. Large-scale structure, the cosmic web of filaments, walls, and voids, emerges naturally from initial quantum fluctuations amplified by inflation. Supercomputers project billions of years ahead, modeling the growth of clusters, the dispersal of galaxies, and the influence of dark energy on cosmic acceleration. These virtual universes allow theorists to test models of dark energy, curvature, and expansion, offering predictions against which future observations can be compared. Yet even in these sophisticated projections, the beyond remains inaccessible, a reminder that measurement, however precise, is bounded by the observable horizon. In the pursuit of these cosmic truths, every instrument and model functions as both a probe and a mirror. Observations reveal the stretching of space and the growth of structure. Simulations provide a laboratory for testing ideas. And yet, the ultimate question, the extent and nature of space beyond our perception, cannot be touched by light, gravity, or computation. Cosmology becomes an art of inference, a careful balancing of empirical evidence and theoretical imagination. Each new dataset, each refined model, illuminates the observable universe, while the unknowable beyond serves as a silent, ever-present horizon, a reminder of the universe's grandeur and the limits of cognition. The tension between measurement and mystery is, perhaps, the defining characteristic of modern cosmology. Instruments extend reach, refine knowledge, and constrain models, yet the question of what lies beyond expansion remains fundamentally unobservable. Space stretches faster than light, galaxies recede beyond detection, and dark energy shapes the universe in ways that can be measured only indirectly. Observatories, telescopes, detectors, and simulations reveal patterns, growth, and structure, yet the full totality of the cosmos eludes capture. This tension is not failure but revelation. The universe is vast, accelerating, and subtly unknowable, and humanity's role is to perceive, measure, and imagine, even at the edge of comprehension. In this unfolding journey, science illuminates without exhausting, measures without defining totality, and predicts without accessing the full canvas. Instruments like James Webb, Vera Rubin, Euclid, and gravitational wave observatories act as extensions of human perception, capturing the cosmic dance across billions of light years. Supercomputer simulations translate these observations into models of evolution and structure, revealing both the logic and beauty of cosmic expansion. Yet all of this occurs within the observable horizon, leaving the domain beyond, a domain that may be infinite, closed, or radically different, forever speculative. The universe is both comprehensible and mysterious, accessible through measurement, yet infinite in implication, a stage where knowledge and wonder intertwine. And so, the pursuit continues. Observations accumulate, models refine, and simulations predict, yet the ultimate question, what lies beyond the universe, remains untouched. In the growing body of evidence, in the silent mathematics of space-time, in the accelerating recession of galaxies, one perceives both clarity and limitation. Humanity has learned to measure the universe with unprecedented precision, to decode its history and dynamics, to test hypotheses about dark energy, curvature, and expansion. Yet at the edge of understanding, the question persists, a horizon that can be approached but never crossed, a cosmic mystery that defines the boundary between the known and the unknowable. Instruments extend perception, data constrains theory, simulations illuminate evolution, and yet beyond these tools lies a space without measure, a reality without boundary, a universe whose totality may forever elude observation. In this tension between the measurable and the unimaginable, science reveals both the majesty of cosmic expansion and the profound humility required to contemplate the unknown. Humanity perceives the universe as it is, yet senses also the infinite possibilities that extend beyond perception, a silent testament to the grandeur, complexity, and mystery of all that exists. In the vast silence beyond the reach of perception, the universe stretches outward, indifferent to comprehension, yet intimately entwined with the consciousness that seeks to measure it. Galaxies drift ever farther, carried by the relentless expansion of space. Their light stretched into whispers of ancient time, and humanity stands upon a fragile world, attempting to grasp the nature of a cosmos that is at once intimate and incomprehensibly vast. Observation reveals motion, acceleration, and structure, yet at the edges of understanding, where light no longer travels and matter retreats beyond causal reach, there remains only speculation, a quiet recognition that some aspects of reality may exist forever beyond perception. This recognition carries with it a profound philosophical weight. The universe, in expanding, is not merely a container of matter and energy. It is a fabric in which existence itself is woven. The idea that there is no exterior, no beyond into which the cosmos grows, challenges intuition and disorients the mind. Space is not a vessel into which galaxies move. Space itself unfolds, stretching in every direction without limit, without center, without edge. The psychological impact is subtle yet immense. Humanity is confronted with the notion of a reality that is simultaneously boundless and finite in perception, where every attempt to define a boundary illuminates the nature of understanding rather than the cosmos itself. In this meditative state, curiosity and humility intertwine. The very human desire to probe, to locate, to contain, meets the profound lesson that the universe does not conform to expectation. Expansion occurs independently of any external medium. Light can recede faster than its own speed across unfathomable distances. The observable horizon defines a finite bubble in an otherwise unknowable expanse. The cosmos, in its accelerating growth, reveals both the power and the limitation of human inquiry. Knowledge is possible, yet ultimate totality remains elusive. There is beauty in this tension, a resonance between the measurable and the inaccessible that mirrors the duality of existence itself. Philosophically, the implications are staggering. If the universe has no exterior, then beyond becomes a concept without meaning. Infinity is not a distant point, but a continuous unfolding, a fabric whose expansion is intrinsic and eternal. In contemplating this, one confronts the limits of thought, the boundaries of imagination, and the fragility of perception. Human cognition, evolved to navigate landscapes with edges, centers, and horizons, now confronts a reality where these intuitions are inadequate. To visualize expansion without exterior is to engage with a universe that is abstract yet profoundly real, mathematical yet poetic, expansive yet intimately connected to the observer who perceives it. The poetic resonance of a universe expanding into nothing is profound. The term nothing here is not emptiness in the conventional sense. It is not a void into which space stretches, but a silence of unbounded possibility. Space is not emerging into a pre-existing container. Rather, expansion is a property of space itself. In this, science and philosophy converge. Observation reveals acceleration and structure. Theory predicts mechanisms and geometry, yet the ultimate substrate remains elusive. In contemplating the expansion of the cosmos, one confronts both the majesty and the terror of a reality that defies containment. A cosmos in which the familiar anchors of comprehension, inside, outside, beginning, and end, are replaced by continuous growth and perpetual unfolding. Here, humility is inseparable from wonder. Each photon that arrives from the distant reaches of space carries a story, a history of expansion and evolution, yet what lies beyond the observable universe is fundamentally unknowable. The search for boundaries becomes a mirror for the human pursuit of meaning. To measure, to theorize, to simulate, is to extend understanding to the limits of perception, yet the universe, in its vastness, offers only questions, not definitive answers. This is not despair, but a meditation on the grandeur of reality, that beauty, complexity, and mystery coexist, and that knowledge and humility are intertwined in the act of inquiry. Cosmic expansion thus becomes a metaphor for human thought. Just as space stretches in all directions, so too does the mind reach for understanding, tracing structures and dynamics, projecting models and speculations, yet always constrained by the observable horizon. The galaxies receding into darkness mirror the journey of contemplation itself. Light stretches, time flows, and every insight reveals new depth and new distance, an unending dialogue between perception and reality. The universe becomes a canvas on which the intellect paints, guided by observation, inspired by speculation, and humbled by the unmeasurable. The interplay of beauty and terror is ever present. Consider the accelerating universe, each galaxy slipping beyond sight, carried by the expansion of space itself, faster than light, unreachable in principle. The cosmos is serene in its vast motions, yet daunting in its scale, indifferent to the human desire for comprehension. To stand in awareness of such expansion is to confront both the aesthetic and existential dimensions of reality, a universe in which the horizon is finite, but the cosmos is boundless, in which distance is measured not only in light years but in degrees of understanding. The emotional resonance of this realization is profound. The universe, in its infinite unfolding, both invites and resists human contemplation. Speculation provides a bridge across this tension. Models of higher dimensional space, multiverse frameworks, and quantum vacuum energy offer intellectual footholds, hypotheses that anchor understanding even as they extend beyond direct measurement. Each theory illuminates a different aspect of cosmic expansion, whether through the subtle pressure of dark energy, the curvature of space, or the existence of parallel universes. Yet each also emphasizes the limits of perception. Instruments can measure acceleration, structure, and curvature, but the ultimate nature of what lies beyond remains suspended in abstraction. In this way, the act of thinking about the universe mirrors the act of observation itself, a balance between what is known and what must remain unknown. Humanity's place within this context is at once central and insignificant. Every attempt to measure the Hubble constant, to chart the distribution of galaxies, to probe dark energy, is a testament to curiosity and ingenuity. Yet the vastness revealed through these endeavors dwarfs any individual or civilization, situating consciousness as a witness to cosmic unfolding rather than a controller of it. The universe is not a stage set for human comprehension. It is an active, evolving fabric whose expansion continues independently of observation or theory. Awareness of this fact carries a mixture of humility and awe, a recognition that the pursuit of knowledge is valuable precisely because it engages with a reality that surpasses human scale. Poetically, the universe receding into darkness becomes a meditation on time, light, and existence. A distant galaxy drifts beyond perception, its photons stretched into redshifted silence, and the observer perceives not just motion, but the passage of eons. Time itself is embedded in this light, a record of cosmic history transmitted across vastness. The stretching of light mirrors the stretching of thought. As perception reaches outward, understanding elongates, dilates, and transforms. In this metaphor, expansion is not only physical but conceptual, a parallel between the unfolding cosmos and the expansion of curiosity, imagination, and contemplation. The ultimate image is cinematic, a galaxy receding into the dark, its light growing faint, stretched, and ancient. Around it, the void is not emptiness, but the unobservable, a silent canvas that frames both wonder and anxiety. Time flows inexorably, space expands relentlessly, and the observer remains suspended between knowledge and mystery, between the measurable and the unmeasurable. The universe, in this final tableau, is both intimate and infinite, comprehensible in part, yet fundamentally unknowable in totality. It is a realm where curiosity, humility, and reflection converge, and where the pursuit of understanding is inseparable from the contemplation of what must remain beyond reach. In this moment of suspended perception, the mind recognizes the duality of existence. Expansion is observable, measurable, and modeled, yet the cosmos is unbounded in principle, with no exterior, no container, and no absolute frame of reference. Infinity is not a distant concept, but a pervasive property of reality. Beyond is not a place but a boundary of cognition. In these reflections, human inquiry meets cosmic scale, and philosophy intertwines with physics, revealing both the majesty and the restraint inherent in the universe. The elegance of expansion, the acceleration driven by dark energy, and the structure traced by galaxies evoke a silent poetry, a narrative in which observation and speculation coexist, each illuminating the other, each constrained by the limits of perception. In the end, the universe expands, and so too does the mind. Observation traces motion and acceleration. Simulation reconstructs structure and evolution. Theory imagines mechanisms beyond immediate measurement. Yet the ultimate frontier remains conceptual, a space defined not by light or matter, but by limits of perception and imagination. The poetic resonance of this realization is profound. The universe invites reflection, encourages humility, and inspires wonder precisely because it extends beyond comprehension. There is beauty in the measurable, terror in the unknowable, and meaning in the recognition that curiosity itself is a bridge to the infinite. The receding galaxy, faint against the backdrop of dark, embodies the intersection of knowledge and mystery. Its light carries history, its motion records expansion, and its disappearance marks the boundary of perception. Yet in the mind of the observer, in the act of contemplation, the universe continues to expand conceptually, offering questions without definitive answers, prompting reflection without conclusion. This duality between the measurable cosmos and the unmeasurable beyond defines the human experience of space, a meditation on existence, time, and the infinite. And so, in the final view, one perceives the universe as simultaneously comprehensible and unknowable, a tapestry of motion, light, and structure, unfolding into the dark. The observer is left suspended between wonder and limitation, contemplating not just the expansion of galaxies, but the expansion of thought, curiosity, and reflection itself. In this suspended moment, the universe is a poem written in light and time, in motion and stillness, in the known and the forever unknown. To gaze outward is to gaze inward, to confront infinity and human scale, to embrace the simultaneous beauty and terror of a cosmos without boundaries, expanding eternally into the silence of possibility. Here, in the quiet stretching of space, the universe becomes a mirror. It reflects both the grandeur of existence and the humility of perception, inviting contemplation of a reality that is infinite, accelerating, and profoundly mysterious. The search for edges mirrors the search for meaning. The act of measurement mirrors the act of reflection. In the receding light of distant galaxies, time flows, space grows, and the mind hovers between observation and speculation, suspended in awe, suspended in wonder, suspended before the ultimate mystery, the universe itself, expanding into the unknowable.